Hi and welcome to this video on benzene. So in this video I am going to be focusing on one of the properties that you see in benzene and how that relates to the reaction of benzene. And after I'll go through the reactions that you need to know for benzene, and we'll finish off with a couple of exam questions. So you can see two skeletal forms of benzene, so this one here or that one there. So either skeletal diagram is okay. And when you do a mechanism for the reaction of benzene, you can use either or, but I would recommend that you choose one mechanism. So choose the mechanism for one of those structures and just be consistent. That just stops you from getting confused and having too many different ways of doing something. So limit it to just one of the mechanisms. When I go through the reaction, I will show both, and then just use the one that works best for you. Now, the reason why we have this diagram over here is because there are actually two resonant forms of benzene. So I've drawn them both here, and you can see that the double bond can be in this position that you see in that first diagram or that position, and they both exist. So what we end up doing sometimes is drawing this hybrid. So this is the hybrid of those two resonant forms. And now that happens because the electrons are delocalized. And the delocalization of the electrons does make the electron density in the pi bonds lower in benzene than what we would see in an alkene, which does mean that benzene is not as reactive as an alkene. So if we look at an alkene, do it over here. So ethene. Now that double bond is going to be an area of high electron density in this molecule, which means if we have an electrophile like bromine, so we'll have an induced dipole. So if we have an electrophile like bromine that approaches this molecule, it is going to be attracted to that area of high electron density, and that reaction will take place spontaneously. Now, because we have a lower electron density in our benzene ring, although you will have the reaction with something like bromine, it does not happen spontaneously with benzene. Okay, so whereas with the alkene, that reaction happens spontaneously, it doesn't happen spontaneously when the molecule approaches a benzene ring, which means in a lot of our benzene reactions, we are going to need some sort of carrier or something that will activate the ring to encourage the reaction. Okay, so we will be focusing on looking at what carrier is used, and you do actually need to know them for your exams. All right, so if we start with that reaction of benzene and bromine. Okay, so I'm going to erase this. So we're adding a halogen, so this is a halogenation of benzene. Okay, I'm going to draw my benzene structure. And we're going to have our Br2. Okay, and in this case, we do need a halogen carrier. So I'm going to write below the arrow that we're going to use aluminium bromide. Oops, that's not a 2. Albr3. Okay, so benzene can only react with halogens in the presence of a halogen carrier. Now, it is important to note that that halogen carrier can be that aluminium bromide, or it doesn't have to be bromide, it's going to be a halide, or it could be an iron halide. right? And what we end up making, we're still going to have benzene, but we're adding a bromine, okay? And if you remember, there is going to be a proton, so hydrogen, that would be there. So we've replaced that hydrogen with the bromine, so the hydrogen will go on to make hydrogen bromide as another product. Right. So that is one of our first reactions of benzene. So some differences that you might notice if this were an alkene, I'll just write it here. If this were an alkene, we would actually make a dihalide. So in this reaction, it's spontaneous, so we don't need a carrier. But you would end up adding both bromines, right? And that's actually off screen, so let me redraw it. There we go, just as a quick reminder of the halogenation of an alkene, you would make a dibromoethane, okay? Whereas in benzene, we're only adding one of those bromines. All right, so that's our halogenation. The next one we're going to do is the nitration. So nitration of benzene, and I am going to go through the mechanism of this reaction. Okay. All right, so there are a couple things to note. I'm going to do the overall equation and then we'll break it down. So for this reaction, we are going to need concentrated nitric acid, and we're also going to need concentrated sulfuric acid. Okay. And we're going to make a nitrobenzene, so an NO2, and water will also be made. All right, so for this mechanism, it is actually first important to know the equation of the making of the electrophile, okay? Or the formation, let's call it a formation of electrophile. Now you don't need to know the use of curly arrows for this, but you do need to know the equation. So the formation of the electrophile, we have that sulfuric acid, H2SO4, and our HNO3. Here, we're going to make HSO4 minus and H2NO3 plus. Okay, and it's this species here, H2NO3 plus, which goes on to our NO2 plus and H2O. So that there is our electrophile. Okay, so that's the making of our electrophile. And you will need to know these equations for the making of that electrophile. Right, so now we're going to go on and show the mechanism of that electrophile reacting with our benzene ring. Okay, so this is, I've specified this as an electrophile, so the mechanism is going to be an electrophilic substitution. All right, so we'll start with showing that hybrid mechanism. So we have our electrophile, NO2, the nitrogen has a plus. And we're just going to show from the delocalized area, we're going to show the area or sorry, the curly arrow. Actually, I'm going to change my curly arrow. It's leaving from the middle. It's going to very clearly point to that nitrogen. Sorry, that got a little bit messy. Okay, and actually it isn't clearly pointing, so let's just not be lazy and make it nice and clear. Okay. All right, so our intermediate from there is going to show that we've broken one of those double bonds, and we're going to have a carbocation. Okay. Then we can show that addition of our NO2, and the other bond that's here is a hydrogen. Okay. So the final step is showing that that hydrogen is going to be leaving. So the shared pair of electrons here is going to move in to that pi system. And we're going to make our final product, which is our nitrobenzene. Okay, so that is one way you can show the mechanism. I'm going to go through and show the other method as well, just in case it works best for you. And then, like I said, choose the one that works best and just be consistent. Okay, so it's not all that different. Okay, except I'm just going to choose one of those resonant forms. So now we have our electrophile. Oops. So I'm going to go from the double bond, going to our electrophile. So our intermediate. Still have that double bond, still have that double bond. And no. 2. We now have our carbocations. Remember, we have that hydrogen there. That is going to be a carbocation. Okay. So I'm now going to show that this bond between that carbon and this hydrogen is breaking, and it's going there. Okay. And then the final product. There we go. All right, so that is the other mechanism. Now, like I said, use the one that you're going to be most confident with. Either one works. This one shows, and maybe it's a little bit easier for understanding that movement of electrons and why the other one works. But you, in an exam, you can use either one. So you can use either skeletal diagram for your benzene. All right, so that is our nitration of benzene. Okay. So the next two reactions I'm going to look at are the fetal cross reactions. So, okay, and the first one is a look at that alkylation. All right, so if we think about alkylation, that word alkylation, we have alkyl, which means we're going to add an alkyl group. Okay, so we're substituting an alkyl group onto our benzene ring. Often you can see alkyl groups represented as just R, and really that's an any length carbon chain. Okay, so CH that is an alkyl group. You can have 2 carbons. And that would also be an alkyl group. Okay, so in our phenyl cross alkylation, we are adding on an alkyl group, and it could be any length carbon chain. Okay, so I am just going to use a generic formula to begin with, and then I'll give a specific example. So in the generic formula, I am just going to use R to represent the alkyl group. So we're going to have our benzene ring. You're going to have your alkyl group, bond it to a chloride, AlCl3 is our catalyst or carrier to help activate that ring. And what we'll make is a benzene ring with the alkyl group substituted on. And remember, there was a hydrogen there, so that alkyl group replaced a hydrogen, which is why it's a substitution. So our hydrogen will go on to make HCl. All right, so if we look at a specific example and actually define what R is, so define our alkyl group, let's say actually, let's just do skeletal because, let's be honest, they're easier. There we go. So that's the reaction. Now the product, it's this chloride that's going to come off. So we're going to be adding 1, 2, 3 carbons. Oops, that's not a benzene ring. So 1, 2, 3 carbons. Okay, I could have written, there's a C there, C, C. That third carbon is what's binding to the chloride. So C, C, C. All right, so I'm going to erase those. So that's our phenyl cross alkylation. So the other phenyl cross that you need to know is the acylation. So I'm going to do that one next. Okay, so here the important part to understand is we're adding, or we're substituting, sorry, I shouldn't have said adding, we're substituting a acyl group onto our benzene ring. Okay, and your acyl group is going to be a carbon double bonded to an oxygen. Okay, so we're going to have some length carbon chain and our carbon double bonded to oxygen. Okay, so that's our acyl group. So if we show an example, and again, I'm just going to do generic first. Again, that's not a benzene ring. Okay, so Cl, we have our carbon double bonded to oxygen, and then some R group, so a certain length carbon chain, AlCl3, and it is going to be this carbon here, so the bond between the carbon and the chlorine breaks, and that carbon will be what attaches to our benzene. Carbon, R group, there we go. Okay, and again, there would have been a hydrogen, and this acyl group replaced the hydrogen that was once bound. So we end up having that hydrogen that binds to that chlorine or chloride, and we make HCl as well. All right, so if we look at a specific example where we're defining what that R group is, AlCl3. So looking at the result of this, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and that is where our oxygen was. So on that carbon there, which is that one there. All right, so that is your fetal cross acylation. So if we look at an exam question now, and actually what I would like you to do is maybe just pause the video and go and write out that mind map that I'd introduced in the first video. Okay, so if you just take the time now, write out the mind map. I know we're focusing on benzene reactions, and those were not in the mind map to begin with, but in any synthesis question, you could have more than one reaction, and you probably will have more than one reaction. So go write out that mind map, and we will use it. So there it is. All our reactions, like I said, the benzene reactions are not on there. If you would like to add them on, okay, so if you want to modify your mind map and you want to add on the benzene reactions, by all means, do that. Okay, I just didn't do that because I wanted this to be a little bit more simplified. But by all means, you can add on those benzene reactions. Okay, make it your own. All right, so let's look at an exam question. Here we go. Draw the structure of the missing compounds in the boxes and add the missing reagents on the dotted lines. All right, so let's break this down. The first step, we had our benzene ring. We can notice what's been added on is a carbon chain with that double bond. So that is related to what we just done, where we've added an acyl group. Okay, so it could be worth your while just making notes on your exam so that you know what change has happened. We've added an acyl group. So straight away you should be connecting this with the fetal cross acylation. So we have 1, 2, 3. 1, 2, 3. The third carbon is where we had that double bond oxygen, and then you would have your chlorine there. Okay, so we've added that group. I've done that a little bit upside down. You could flip it around. That's up to you. Either way, it's going to be right. Potentially, you might want to make it fit into the box a little bit better than what I did. Okay, now the conditions, AlCl3 for your fetal cross acylation. Okay, so that's that bit done. So the next one is looking at what happened from this intermediate going to our next intermediate or our next compound. So we've had basically this carbon double bonded oxygen is a ketone. And we've gone from a ketone to an alcohol. So this is where it's handy to have written out that my map. So we identify where we have our ketone going to our alcohol, where we're reducing. So we're reducing that ketone. We can see in our mind map that that's NaBH4 and water is the final proton source. Very likely what they're looking for here though is NaBH4 and H2O. Instead of H2O, you potentially could have just said NH+. So knowing that, there would have needed that final proton in the end as well. I'm going to stick with H2O. All right, now looking at this intermediate to our final product, where we've had an alcohol now become an alkene. So again, looking just at our mind map, alcohol to alkene, we have the conditions, we have the reactant, so easy peasy, steam, so H2O, H3PO4, and heat, so 300 degrees C. So we can go and write that on there. Steam, H3O4, 300 degrees C. Okay. Sorry, I shouldn't have removed that. There we go. And that is that question done. Okay. So anytime you have a synthesis or a flow chart question like this, just break it down into smaller bits and reason through it. Okay. Right, so before I go on to the next exam question, I am going to go through some benzene derivatives and the 2,4,6 directing and 3,5 directing. Okay, so we have 2, 4, 6 directing groups. Oops. Which is, I'm not going to have space, when you have an amine, so NH2 on that benzene, or an OH on that benzene. Now both of these groups, NH2 and OH, are electron donating groups. So NH2 and OH are electron donating groups. So what that means is their electrons can be donated into this benzene ring system. Okay, and that will make there be a higher electron density on the positions 2, 4, and 6. Okay, so higher electron density at the 2, 4, and 6 position. Okay, which means those are the positions that are more likely to react. Okay, and then if we have a substitution reaction that takes place, or anything that's going to react onto that benzene, it will be added to the 2, 4, or 6 position. So if we just look at, let's see, bromination, so reacting these with bromine, you would need excess bromine. Okay, so with that one there, bromine ring, or sorry, not bromine, benzene ring. You'll have a bromine added to the 2, so 1, 2, 3, 4. Off screen, 4, 5, 6 position, and it's the same thing with this one here. Now we're going to talk a little bit more in the next video on this particular molecule, so phenol. Okay, but I'm not going to go much more into it here. All right, so that's our 2, 4, 6 directing groups. And then why? Okay, just that change in electron density. So next, let's look at our 3, 5 directing group. It is important to note that your 2, 4, 6 directing group, because you end up having a higher electron density, those reactions do tend to happen a little bit more spontaneously. In contrast to this 3,5 directing, so when you have NO2, so nitro group. Now what happens with the nitro group is your NO2 is electron withdrawing. So this is pulling electrons out of that pi system, so away from the benzene ring. And that results in positions 2, 4, and 6 to have a lower electron density, okay? So instead of a higher electron density, we're ending up with a lower electron density. All right, so that 2, 4, 6 have a lower electron density, which means anything that's reacting with this molecule is not very likely to react in any of those positions, which means they will react in the 3, 5 position instead. But it also means, because we're withdrawing electrons, it does mean that this nitrobenzene, you are going to need some sort of carrier to help this reaction go on. So if we looked again at bromination, so Br2, you are going to need something to encourage that reaction. So AlBr3. Actually, I'm going to change this so it goes this way so that we can actually see what's going on. So above the arrow, Br2. Okay. So our product, bromine at the 3 and bromine at the 5 position. There we go. All right, so that is our 2, 4, 6 directing and 3, 5 directing groups. So from there, I am going to do another exam question. Okay. And hopefully you still have your mind map handy. All right, so I did write this out because I did modify it. I made it harder than what it originally was on an OCR exam. But hopefully we can still work through it because you potentially could have something this hard. Okay, so you need to prepare yourself be able to do something challenging like this. So complete the full flow chart by showing the missing organic structures in the boxes, naming the mechanism, and stating the reagents on the dotted line. All right, so first thing, we're going to look at what we started with, and we're going to look at our final product so that we know where we need to go. So first thing you should notice is that nitro group, NO2, has been reduced to an amine. Okay, so we know at some point we need to reduce our NO2 to an NH2. Okay, the other thing to note is we've added a bromine. Okay, or we've substituted on a bromine. So bromination has also taken place. So does the bromination happen first, or does the reduction happen first? Oh, that's not even on screen. So let's move this over. Not that it was massively important, but we have our two reactions, bromination and reduction. So which is going to happen first? So if we think this through, we know NO2 is a 3,5 directing. And we know NH2 is a 2, 4, 6 directing. the bromine has been added to the 1, 2, 3rd carbon. So we need a 3, 4 or 3, 5 directing, which means the bromination, we needed to have an NO2 on our benzene ring for that bromine to end up on the 3rd position. So our first step is going to be a bromination. Now this would be an example of an electrophilic substitution. So specific, we're substituting, so we're removing a hydrogen, substituting on a bromine. And it originally would have been attracted to an area of electron density. Okay, so electrophilic. So it's something attracted to the electrons, and we're substituting it on. They potentially would have accepted bromination. Okay, but you're never going to be wrong if you fully specify the type of substitution. Okay, so electrophilic substitution, thinking back to our reagents, well, we need Br2. This is an electron withdrawing group, so we also need the AlBr3. Okay, so those are our reagents for the first step. Now our intermediate, that nitro group is still there, but we would have substituted on a bromine in that 3rd position, which means our final step is reducing that NO2. Okay, so reduction. If you can't quite remember the reduction, I've lost my mind map. Okay, you can pull out your mind map. Okay, we have on here your nitroarine being reduced to an amine. Okay, and we need concentrated hydrochloric acid and a tin catalyst. So what we're going to do on here, conc HCl / SN for your tin. You will need both of those. Okay, that's why I'm really stressing that mind map, because you do need all the reactants in an answer. Okay, so you do need both. And what's it called? Well, we said it's a reduction. That is a reduction reaction. And that's that answer, or question answered. Okay. All right, so I hope that was useful. I am going to stop it there. If you have any questions, you can leave some comments. Like I said, the next video is going to be on phenols. It's probably going to be a quite short video. But if ever you need me to elaborate, leave a comment. I'm happy to post a follow-up video, or just answer, if can be, just answer in the comments section. All right. Good luck with your studying. Remember, you are awesome and you totally have this. Bye.